All right, so you're going to be having to pause the video regularly to take down the note. A matrix or matrices are rectangular arrays of numbers. Computer science backgrounds, you guys define variables that are arrays, I'm sure. Here's an example of an M by N matrix that has M rows, so that's going down, and N columns. Now, we use a large square bracket to enclose that, and it's matrix A. We usually use a capital letter to designate a matrix. And the numbers in each row are not separated by commas, they're just separated by spaces. Okay, so N columns. So we designate an element of the matrix by subscripts. So A sub 1, 1 means row 1, column 1. So all the way to the right of the first row is A sub 1n. If you do end up going to two-digit numbers and stuff like that for column numbers and row numbers, your subscript could have commas in them as well. We're not going to do anything that big. We're going to be doing today 3 by 3 matrix is the largest we'll do. When we go to solve systems using row reduction, row echelon form, and that sort of thing, we'll be doing a 4 by 3 matrix, 4 columns and 3 rows. Okay, there we go. So row number first and then column number. A 2 by 2 matrix, so pause the video, copy that down if you need to, what a matrix is. A 2 by 2 matrix, there you go. And then we have something I mentioned before, determinants. Well, here I'm introducing determinants. The determinant, or det, right, is single vertical line, looks like absolute value bars of A11, A12, A21, and A22. And again, it's the diagonal, that diagonal minus that diagonal is the idea to get the determinant of A. Okay, so again, pause the video, take your notes. Now, applications of determinants and matrices. So we just did in the last lesson area of a parallelogram, and it was the cross product. And we'll do this example, and you'll take your notes, and then we'll do the example using the cross product like what we had before. So the vector components of a matrix, there you go, are 2, 4, and 5, 2. The determinant of A is the determinant of the matrix A. There we go. We do 4. 2 times 2 is 4, minus 4 times 5, which is 20, negative 6, and of course area is positive. This should be the same as A cross B, magnitude of, right? So A isn't 2 and 4. A would be 2, 4, and 0. And B, the no Z component, because it's two-dimensional, would be 5, 2, and 0. So if we're doing the cross product using our normal algorithm for that, we list the components of the vector. And we ignore the first column. We get 4 minus 0, which is 0. 0 minus 0, which is 0. And finally, 4 minus 20, which is negative 16. Take the magnitude of that, we get the square root of 16 squared, which is, again, 16, same thing. So what's the advantage? Not much. Okay. But we're introducing matrices and determinants. 3 by 3 matrix, there we go. Again, row number and the subscript comes first, and then column number. And then we have something called the rule of Cyrus, and this was actually relatively new for me. I learned this a few years ago. I didn't learn this when I was a student. I learned this when I was a teacher. What you do is you take, to find the determinant, the value of the determinant for matrix A, you follow the rule of Cyrus, which you take the blue diagonals, and you find the product along those blue diagonals. So you take A11 times A22 times A33, and you add those 3 diagonals together, going down to the right, and subtract the 3 diagonals going up to the right. Okay, that's what we're showing here. And that's the value of the determinant. Now, what's the application for this? So, take your note, finish your note on that, and then go on. Well, it turns out that the determinant of parallelepiped is the volume of the determinant of A is the volume of the parallelepiped defined by those three matrices. And if the volume is 0, the vectors are coplanar. So again, take your note and then go on to the example. I think we'll just do one. So copy down the example. Okay. I want you to do the triple scalar first, conventionally. So do B cross C first, and then dot that with A. Okay. So when you have that, go ahead and run the video, and I'll go through it. A is 1, 2, and 3. B cross C, I have down that we have -1, -2, -5. Okay. Of course, it's absolute value because it's positive. Then we dot these out. We get -1, -4, -15, which is -20, which is 20. So that's how we were doing it before. So these vectors are not coplanar, and the volume of the parallelepiped is 20. Now we're going to practice the rule of Saros instead. So the rule of Saros, you list the elements of A. So this is very similar to what we did for cross product, I guess. Then we list the elements of B. And again, which order you do it in doesn't matter because the three, remember the proof, the three triple scalars give the same quantity. So it doesn't matter which order you do it in. 3, -4, and 1. Make sure I have those right. Okay. So I'm going to go ahead and multiply here. I have 3 plus -6 plus +12 minus 27 that's 4, so -4, and that's -2, so +2, or well, I'll show it as a minus -2. When we do all that, we get -3 plus 12 is +9, minus 18, minus 22, minus 6. What did I do? I guess that's good. So -3, minus +9, minus 18, minus 22, plus 2 is 20. I get 16. So that's -20. Volume is the determinant of A, which is -20, which is 20. So does the rule of Saros save that much time? Not really. But now you know what? Another method. And that's it.